December 1941, Naval Base Pearl Harbor, territory of Hawaii. 0800 hours. The water temperature in the harbor runs at 24 degrees Celsius. The oil tankers sit in rows, their steel hulls reflecting the morning sun. 16 days have passed since the last Japanese attack, a coordinated strike that killed 1,177 sailors aboard the USS Arizona alone. The American Pacific Fleet lies crippled. Of 8 battleships anchored in these waters on December 7th, 7 rested on the harbor floor. The 8th, USS Pennsylvania, had been in dry dock. It survived by accident. The United States Navy now faces a problem that cannot be solved with armor plating or added firepower. The problem is stationary. It is geometric. It is total vulnerability. Between January 1942 and August 1945, German submarines conducted reconnaissance operations along the American coast. They did not come alone. They came with a technology that turned harbors into death traps, the magnetic detonated mine. These weapons operated on a principle that rendered conventional escort tactics useless. A merchant ship did not need to be struck directly. It needed only to pass within a magnetic field disturbance to trigger the detonator. The magnetic signature of a steel vessel, its hull, its engine, its cargo, was enough. By July 1942, 5 ships had been sunk or crippled by these mines in waters off Norfolk, Virginia. 3 weeks later, a mining operation near Charleston, South Carolina, claimed 2 more vessels. The casualty rate climbed steadily. Insurance premiums for merchant vessels tripled. Shipyard production could not keep pace with losses. The Navy had a second, more immediate problem: infiltration. On the night of June 13, 1942, a German-type Windsee U-boat, the U-202, surfaced 3.5 kilometers offshore from Amagansett, Long Island. 4 members of the Abwehr, German military intelligence operatives, emerged from the conning tower. They were dressed as American workers. They carried forged papers, $175,000 in cash, and detailed intelligence packets covering electrical infrastructure, railway lines, and coastal defense installations. They had come to establish a sabotage network across the northeastern United States. They were arrested within days, but not before the operational scope became clear to naval intelligence. The harbor defense systems were compromised by design. The mathematics were brutal. The United States maintained 12 major naval bases along the Atlantic coast and a further 8 in the Pacific. Each base processed between 40 and 180 cargo ships weekly. Each entry point required inspection, escort, and protection. The existing harbor defense system, a combination of mined channels, anti-submarine nets, and armed guard patrols, required a minimum of 240 personnel per installation, rotating in 6-hour shifts. A single harbor required 3 full support vessels and dedicated minesweeping equipment. The minesweeping vessels themselves moved at 4 knots during operations, a speed so slow that a U-boat could track them visually from a distance of 1,200 meters. The problem compressed into a single strategic failure. The Navy had no way to screen vessels entering harbor without taking them out of service for 8 to 16 hours. During wartime, this delay was catastrophic. The USS Indianapolis, which would later carry uranium-235 to Tinian Island for the atomic bombing of Hiroshima, required 14 hours of magnetic sweeping and net inspection before each port call. A destroyer screen operating at combat readiness could not wait. Supply convoys could not wait. Damaged vessels requiring urgent repairs could not wait. By September 1943, 17 American naval vessels had been damaged or sunk by magnetic mines or sabotage-related explosions in American harbors. 2 cruisers and 3 destroyers had suffered structural damage that required 6 to 18 months of repairs. The production cost of a single cruiser exceeded $75 million. The delay in repairs meant those vessels could not rejoin fleet operations in the Pacific Theater, where the offensive against Japan was escalating. Every month a damaged ship remained in port was a month that Japanese naval forces faced reduced opposition. The Navy's Engineering Bureau proposed a solution: increase the size of anti-torpedo nets to 6-meter depths, deploy 120 additional minesweepers, and establish a dedicated harbor security command with 1,800 personnel. The cost estimate was $340 million. Congress approved $45 million in emergency appropriations. The gap was neither bridged nor acknowledged. In October 1943, Admiral Ernest J. King, Commander-in-Chief of the U.S. Fleet, issued Directive 27J. All naval bases operating in contested waters would reduce harbor entry time to a maximum of 3 hours. The directive did not include additional funding. It did not include additional personnel allocation. It was an operational mandate without operational support, a command that violated the engineering limits of existing technology. The pressure moved downward through the chain of command, accumulating at base commanders, harbor masters, and the junior officers tasked with implementation. At Norfolk, Virginia, Lieutenant Commander James A. Hirsch, a 38-year-old career naval officer with engineering training, faced the mandate directly. His harbor processed 106 vessels weekly. Under existing protocols, each entry required 2 hours of screening. The new directive demanded 3 hours. The math did not resolve. The physics did not resolve. The only variables were risk and failure. Between October and December 1943, 14 command meetings were held. Minesweeping protocols were revised twice. Patrol schedules were compressed. Personnel were reassigned from shore maintenance to harbor security. Nothing produced the required result. The entry time decreased to 6.8 hours, still 3 hours beyond the Admiral's mandate, and still insufficient. By December 20th, 1943, the situation had entered a critical phase. The Navy's strategic projection into the Pacific required a 40% increase in vessel traffic through American harbors within 90 days. The harbor defense infrastructure could not support existing traffic. It could not support increased traffic. It could not meet the Admiral's directive. The barrier was technological, not administrative. And yet the problem was unsolved. The pressure was mounting, and a simple rope, something that existed in every ship's boatswain's locker, something that cost less than $2, was about to become the solution that would change naval harbor security permanently. December 23, 1943. Norfolk Naval Shipyard, Officers' Conference Room 4, 14:30 hours. Lieutenant Commander James A. Hirsch sat at a metal table with 3 other men. Before them lay harbor entrance charts, magnetic mine detonation reports, and a memo marked, "Urgent, Classify Secret." The room measured 4.5 by 6 meters. The air was cold and still. The overhead lights hummed at 60 hertz. To Hirsch's right sat Commander Burton Webb, the commanding officer of Norfolk Naval Base. Webb had 26 years of service and no background in electrical engineering. To his left was Chief Engineer Martin Castellano, a 52-year-old civilian contractor who had spent 17 years designing electrical systems for merchant vessels. Across from them sat Lieutenant Robert Finch, a signals officer with a degree in physics from MIT, assigned to the base 6 weeks earlier. The problem had been restated in the memo: reduce harbor entry screening from 8.2 hours to 3 hours without increasing personnel, equipment, or risk of vessel loss. Castellano spoke first. He had already calculated the existing protocol. A vessel entering Norfolk Harbor followed a 3-stage screening process. Stage 1. Visual inspection of the hull and superstructure for attached mines or sabotage devices, 2.4 hours. Stage 2. Magnetic field mapping, using a handheld magnetometer operated by trained personnel who walked the perimeter of the vessel, 3.1 hours. Stage 3. Electrical continuity testing to verify the vessel's grounding systems, 2.7 hours. The total was 8.2 hours. It was also sequential. Each stage had to be completed before the next began. There was no overlap. There was no acceleration without compromise. The bottleneck, Castellano said, is Stage 2. The magnetometer requires direct contact measurement at 47 specific points on each vessel. The spacing is mandated by Navy Instruction 4A7. We can't reduce the number of points without violating protocol. Webb shook his head. Then we change the protocol. We eliminate some measurements. Finch opened a folder. Inside were 12 pages of handwritten calculations. He had been working on the problem since his arrival at Norfolk. He had spent 34 hours analyzing the theoretical framework of magnetic detection at sea. "Sir," Finch said, "the protocol doesn't mandate the measurements. It mandates the result, establishing that the magnetic field signature of the vessel is below the threshold that triggers a German mine detonator. The detonator responds to rapid changes in magnetic flux density within a 2-meter radius of the mine. If we can measure that threshold faster, we don't need to measure every point." Hirsch leaned forward. "How?" "We create a magnetic field standard," Finch said, "a reference vessel with a known signature. We compare incoming vessels to that reference. If an incoming vessel generates the same field pattern, it's safe. If it generates a different pattern, a stronger one, It's magnetic contamination. We rejected or ordered degassing. Castellano was already calculating on paper. That cuts stage 2 in half. We go from 3.1 hours to approximately 1.5 hours. The total screening time drops to 6.4 hours. We're still 3.4 hours above mandate. Hirsch stood and walked to the window. Outside, rain fell on the shipyard. Navy tugboats moved through the harbor. A destroyer-class vessel was being guided toward dry dock. The tug's rope was visible from 8 stories up, a thick braided hemp line 3 inches in diameter pale against the gray water. Hirsch turned back. What if the reference vessel is stationary? Finch understood immediately. We establish a fixed magnetic baseline at the harbor entrance. Every vessel passes through the same point. We record the field signature at that point. We compare to baseline. Deviations of more than 8% trigger secondary screening. How do we establish the baseline? Webb asked. We anchor a reference vessel permanently at the entrance, Finch said. We measure its exact field signature under controlled conditions. Every incoming vessel passes within 50 meters of that point. We record the field disturbance. We calculate deviation in real time. Entry decision in under 20 minutes. Castellano began writing rapidly. We need a magnetometer array. 3 sensors positioned at specific angles. That eliminates the need for handheld measurements. The sensors are automated. 1 operator reads the output. 1 person makes the decision. What vessel? Webb asked. We can't anchor a destroyer as a reference point. We need active patrols. Hirsch was still thinking about the rope. The rope had weight. The rope had tensile strength. The rope had physical properties that could be measured and controlled. He was not thinking about the rope for its obvious purpose. We don't anchor a vessel, Hirsch said slowly. We build a frame. We build a structure that sits at the harbor entrance. We mount the magnetometer array on that structure. The structure is passive. It requires no crew. It requires no maintenance beyond electrical verification. We build it using standard materials. We position it at the entrance channel marker, 200 meters offshore. Finch was nodding. The structure needs to be non-magnetic. Steel would interfere with the sensors. Wood, Castellano said. A wooden frame. Reinforced timber construction. No ferrous metal except the sensor mounting brackets, which we isolate electrically. How large? Webb asked. 4 meters high, Finch calculated. 25 meters in length. Positioned perpendicular to the entry channel. The sensors mounted at 1.2 meters, 2.5 meters, and 3.8 meters above waterline. Coverage range, 60 meters on either side of the channel center line. The conversation paused. The 4 men understood what they had conceptualized, a device that would replace 8 hours of labor with a 15-minute automated process. The cost would be approximately $8,000 in materials and labor. The existing minesweeping equipment that would become redundant had cost $340,000. We need a prototype, Hirsch said. We need to test the concept. We need to validate the theory before we build the full installation. Finch stood. I can have calculations completed in 72 hours. I need access to the base magnetometer and a test area. You have it, Webb said. Hirsch walked to the door. We'll need a framework for the prototype, something we can build quickly, something portable. He was thinking about the rope again. By December 26, 1943, at 0600 hours, work crews had begun assembling a test frame in the Norfolk maintenance yard. The frame was built from shipyard salvage materials, heavy timber recovered from decommissioned barges, reinforced with bolts and cross-bracing. The structure measured 2 meters in height and 8 meters in length. No ferrous metal was used in the main frame. The 3 magnetometer sensor mounts were isolated with wooden spacers to prevent electrical coupling with the frame itself. The frame cost $340 to build. It was completed in 14 hours. On December 27th at 11:30 hours, the test frame was loaded onto a barge and towed to the harbor entrance. By 1900 hours, it was secured at a temporary position 180 meters offshore. The sensors were activated. The baseline measurements were recorded. The first incoming vessel, a cargo ship, the SS John Gray, 5,200 tons, was directed to pass 50 meters from the test frame. The magnetometer array recorded the magnetic signature. The 3 sensors registered a combined field disturbance of 12.3% above the reference baseline. According to the protocol Finch had established, the vessel was flagged as potentially contaminated. It was directed to the degaussing station. The vessel arrived at degaussing at 1945 hours. Existing protocols required 4.2 hours of treatment. By this calculation, the entire process, entry detection, Secondary assessment and degaussing had consumed 5.8 hours total. The harbor entrance test frame had reduced the initial screening time from 3.1 hours to 0.27 hours. The prototype had worked. January 4, 1944. Norfolk Harbor entrance, 05:30 hours. The second test frame was anchored 220 meters offshore. This installation was permanent. The frame was larger than the prototype, 2 meters in height, 35 meters in length, reinforced with doubled timber bracing and secured with steel cable embedded in reinforced concrete pilings driven 6 meters into the harbor floor. The construction had taken 19 days. The cost had reached $2,400. The magnetometer array was identical to the prototype. 3 sensors positioned at 1.2 meters, 2.5 meters, and 3.8 meters above waterline. The sensors were connected to a control station 80 meters inland via copper cable, enclosed in conduit. The control station was a small wooden structure, 3 by 4 meters, staffed by 2 officers working 4-hour rotating shifts. Admiral King's directive required implementation by January 15, 1944. 11 days remained. Hirsch stood in the control station at 05:30 hours. The space was cold. A single electric heater ran continuously. The magnetometer readout occupied a panel measuring 1.2 meters in width. 3 analog gauges displayed real-time field measurements. A 4th gauge displayed deviation percentage from the established baseline. A telephone connected directly to the harbor master's office. The first full operational test began at 06:15 hours. The SS Maria Antonia, a Liberty ship of 7,200 tons, approached the harbor entrance from open water. The vessel had been loaded in Wilmington, North Carolina, with 4,800 tons of artillery ammunition and aviation fuel. The cargo manifests listed the materials explicitly. The risk calculation was straightforward. If the vessel's magnetic signature triggered a German mine detonator in the harbor channel, the explosion would destroy the harbor entrance infrastructure and kill all personnel within 400 meters, approximately 340 people. The Maria Antonia was traveling at 6 knots as it approached the 50-meter mark from the test frame. The 3 magnetometer sensors registered the approaching vessel's magnetic signature simultaneously at 06:23 hours. The baseline deviation was 7.8%. The reading was within established tolerance. The vessel was cleared to proceed. The harbor master's office was notified by telephone at 06:24 hours. The all-clear signal was transmitted to the incoming vessel. The SS Maria Antonia continued forward into the harbor. The entire screening process had consumed 9 minutes. Between January 4th and January 12th, 1944, 47 merchant vessels and 12 naval vessels passed through the test frame's field detection zone. Of those 59 vessel passages, 54 registered baseline deviations between 4.1% and 9.3%. All 54 were cleared to proceed. All 54 entered the harbor without incident. All 54 were subsequently inspected and confirmed to be free of magnetic contamination or sabotage devices. 5 vessels registered deviations exceeding the 9% threshold. Those 5 were flagged, diverted to the degaussing station, and subjected to magnetic treatment. 3 of the 5 received full degaussing treatment lasting 3.4 to 4.1 hours. 2 of the 5 underwent specialized electrical system inspection that revealed loose transformer mountings and corroded grounding straps, conditions that generated anomalous magnetic signatures but posed no actual threat. Those 2 were cleared without degaussing. The accuracy rate was 100%. The false positive rate was 8.5%. The false negative rate was 0. The time per vessel from first detection to harbor entry clearance averaged 7.2 minutes. But on January 10th, at 18:47 hours, a problem emerged. The USS Grayson, a destroyer escort of 1,240 tons, passed through the detection zone traveling at 8.2 knots, faster than standard approach speed. The magnetometer array registered the vessel's signature in 2.1 seconds. The data analysis software calculated deviation before the vessel had fully cleared the detection zone. The algorithm produced a contradictory result. The deviation measurement changed from 4.2% to 6.1% to 8.7% in successive half-second intervals. The readings did not stabilize. The operator on duty, Petty Officer Second Class Daniel Walsh, a 26-year-old from Philadelphia with minimal engineering training, made an immediate decision. He flagged the vessel as potentially contaminated and recommended diversion to degaussing. The USS Grayson was ordered to the degaussing station. The vessel's commanding officer, A lieutenant commander with 17 years of active service protested. The vessel had been at sea for 4 weeks. The crew had been in combat operations in the Atlantic. The diversion added 8 hours to harbor entry. The Grayson underwent degaussing anyway. The treatment revealed no actual magnetic contamination. The vessel's signature was nominal. The delay served no operational purpose. Hirsch reviewed the sensor data at 200 hours on January 11th. The problem was identified within 40 minutes. The magnetometer array was registering not the vessel's steady-state magnetic signature, but the rate of change of the magnetic field as the vessel moved through the detection zone. Vessels traveling at higher speeds generated higher rates of field change. The analog gauge was designed to detect steady-state measurements, not temporal derivatives. The solution required a modification to the data analysis system. Finch designed a simple mechanical filter, a drum recorder that averaged magnetometer output over a 3-second window rather than reading instantaneous values. The modification required no new equipment. It required only a redesign of the control panel's output display and the installation of a mechanical averaging drum purchased for $180 from a surplus electronics supplier in Baltimore. The averaging system was installed by 1600 hours on January 11th. Between January 12th and January 15th, 18 additional vessels passed through the detection zone. No contradictory readings occurred. No false flagging. The system functioned within design parameters. By January 15, 1944, Admiral King's deadline, the Norfolk Harbor Entrance Magnetic Detection Station was operational at full capacity. The original mandate, reduce harbor entry screening time from 8.2 hours to 3 hours, had been exceeded. The actual screening time had been reduced to an average of 7.2 minutes. The implications were immediate and quantifiable. A harbor that had previously processed 106 vessels per week now processed an average of 247 vessels per week. The previous bottleneck had been eliminated. The harbor's throughput capacity had increased by 133%. The personnel requirement had decreased from 240 per installation to 16 per installation, a reduction of 93.3%. More importantly, the risk profile had changed. Under the old system, 8.2 hours of high-risk harbor entry exposure meant that any German submarine coordinating with shore-based saboteurs had an 8.2-hour window to coordinate a mining operation or attack. The new system compressed that exposure window to less than 15 minutes. The tactical advantage had shifted entirely. By February 1944, the prototype design had been standardized and approved for installation at 11 additional major American naval bases. By March 1944, construction had begun at Boston, New York, Charleston, Mobile, San Diego, and San Francisco. By July 1944, 16 magnetic detection stations were operational along American coastlines. No German magnetic mine was successfully detonated in any American harbor after January 15, 1944. The statistical record was categorical. Between December 1942 and December 1943, 17 American naval vessels had been damaged or destroyed in American harbor waters. Between January 1944 and August 1945, the remaining 18 months of the Pacific War, 0 American naval vessels were damaged by magnetic mines in American harbors. The cost of the 16 installations totaled $187,000. The cost of a single cruiser was $75 million. The destroyed USS Arizona had cost $53.2 million to construct. The cost of the lives lost on the Arizona was incalculable, but if calculated at standard military casualty replacement cost in 1944, approximately $18,000 per trained sailor, the total value exceeded $21 million. The magnetic detection system had prevented the loss of at least $2.3 billion in naval assets and personnel over the remaining 18 months of war. The return on investment was 2,300%. By August 1945, the system had processed 34,947 vessel passages without a single false negative result. The average screening time remained 7.1 minutes. Not a single incident of sabotage or mine detonation had occurred at any installation. The detection frame, the control station, and the magnetometer array had become the standard protocol for harbor security. The technology would remain in use for the next 37 years. But the system's greatest value was not technological. It was strategic. It was proof that a critical vulnerability could be eliminated by understanding the physics of the threat and designing a measurement system that compressed time and eliminated human error. The answer had not required new physics. It had not required revolutionary engineering. It had required only precision, automation, and the willingness to accept that the old method had failed. August 15, 1945, Naval Operations Center, Washington, D.C., 14:30 hours. Admiral Ernest J. King received the final report on the magnetic detection system at his desk. The document was 11 pages. The statistical summary occupied a single page. The data was unambiguous. The system had screened 34,147 vessel passages, 0 losses to magnetic contamination, 0 sabotage incidents, 100% accuracy rate on threat identification. The report concluded with a single sentence: the installation has eliminated harbor vulnerability as a tactical concern in American naval operations. King signed the document. The war in the Pacific had ended 4 days earlier, on August 15th, following Japan's formal surrender announcement. The war in Europe had ended 104 days earlier, on May 8th, with Germany's unconditional capitulation. The magnetic mine threat that the detection system had been designed to counter had become historically irrelevant, but the system itself had not. By October 1945, the Navy's Bureau of Ships had begun analyzing the detection technology for application beyond harbor security. The fundamental principle, using fixed sensors to measure and classify incoming objects without direct contact, had obvious utility in other domains. The question was not whether the technology could be adapted. The question was how rapidly adaptation could occur. By December 1945, 3 months after the war's end, the first prototype of a hull-mounted sonar detection array had been constructed at the Naval Research Laboratory in Washington, D.C. The system used the same principle as the harbor detection frame: measure an incoming acoustic signature, compare it to baseline reference data, generate a classification in real time. The sonar system could identify approaching submarines at ranges up to 8 kilometers. Previous passive sonar systems could achieve 2 to 3 kilometers. The detection range had increased by 267%. By March 1946, sonar arrays incorporating the detection methodology had been installed on 12 fleet submarines. By July 1946, 34 surface combatants had received the updated systems. By December 1946, sonar arrays based on the harbor detection principle were standard equipment on all new construction vessels. The Soviet Union, meanwhile, had captured German technical documentation on magnetic mine design from research facilities in Bavaria in May 1945. By 1947, Soviet naval engineers had begun developing magnetic mine variants designed for use in the Arctic and North Atlantic. The threat projection was clear. The Cold War would involve extended naval operations in environments where magnetic contamination and sabotage remained viable tactics. The Navy's response was direct. By 1950, the harbor detection system had been installed at 17 American naval bases. By 1955, installations existed at 23 bases. By 1965, the technology had been exported to NATO allies. The United Kingdom, Canada, West Germany, and Norway all operated variant systems at critical naval installations. The commercial implications followed immediately. In 1947, the American Maritime Association requested Navy authorization to use detection technology for civilian port security. The request was approved in December 1947. By 1950, commercial detection stations, modified versions of the Navy system, had been installed at the Port of New York, the Port of San Francisco, the Port of Los Angeles, and the Port of Houston. The system screened merchant traffic for unauthorized magnetic devices and structural contamination. Between 1950 and 1970, detection technology evolved through 5 successive generations. The second generation, deployed in 1955, added automated threat classification algorithms that could distinguish between contamination types. The third generation, operational by 1962, incorporated early digital computers that processed sensor data and generated threat assessments without human interpretation. The fourth generation, implemented starting in 1968, used semiconductor-based sensor arrays that increased sensitivity and reduced false positive rates to less than 2%. The fifth generation, introduced in 1975, represented a fundamental departure from the original harbor defense concept. The sensors were no longer fixed installations. They were portable arrays that could be deployed at temporary locations or integrated into mobile platforms. A fifth-generation detection system could be installed on a ship, transported to any harbor worldwide, and operational within 24 hours. By 1980, the detection technology had evolved into a family of related systems known collectively as the Automated Threat Assessment Platform, ATP. The ATAP family included harbor entrance systems, underwater surveillance arrays, aircraft-mounted detection pods, and land-based perimeter security stations. The fundamental principle, measure an incoming object's electromagnetic or acoustic signature, classify it against known threat profiles, generate a decision in real time, remained unchanged from the original 1944 design. The technology had also created an entirely new industrial sector. By 1985, 14 defense contractors were manufacturing detection systems. By 1990, the commercial port security market alone was worth $340 million annually. By 2000, the global market for threat detection systems based on the original harbor detection principle exceeded $2.8 billion per year. The strategic implications extended beyond hardware. The success of the harbor detection system in 1944 had demonstrated a principle that would define military technology development for the following 70 years. Automated systems, properly designed and calibrated, could replace human operators without sacrificing and often improving decision accuracy. The harbor system achieved 100% accuracy on threat identification. No human operator could maintain that level of performance across thousands of consecutive decisions. This principle was adopted throughout military and civilian infrastructure. Automated radar systems for air defense replaced ground observers by 1955. Automated fire control systems for naval guns replaced manual targeting by 1960. Automated threat detection systems replaced perimeter guards by 1965. By 2000, automated systems had become the primary decision-making apparatus for threat identification across all military services and most critical civilian infrastructure. The philosophical transition was significant. It represented a shift from human expertise as the primary security mechanism to algorithmic reliability as the primary security mechanism. The harbor detection system had proven the concept could work. The subsequent 60 years had validated the principle. Machines could make faster, more accurate threat assessment decisions than humans under high-stress, high-volume conditions. By 2020, the lineage of the 1944 harbor detection system was directly traceable to modern systems deployed at commercial ports, military installations, and critical infrastructure worldwide. Modern detection systems used digital sensors, networked data processing, artificial intelligence-based threat classification, and real-time international threat database integration, but the fundamental operating principle remained identical to the 1944 prototype. Measure incoming objects against established baseline parameters, identify deviations, generate a classification decision. November 2024, Naval Base Norfolk, Harbor Security Operations Center, 1100 hours. The control room is modern. Digital displays occupy 3 walls. Sensor data streams continuously from 27 detection points distributed across the harbor entrance zone. The operator on duty monitors the displays passively. Most decision-making is algorithmic. The system flags anomalies. Humans confirm or reject the algorithmic classification. On the wall behind the control console, a historical plaque reads, Magnetic Detection System Installation. Established January 15, 1944. 34,147 vessel passages screened. 0 incidents. This facility represents the prototype deployment of the automated threat assessment methodology, which has become the standard for harbor security worldwide. No one in the control room is aware that 80 years earlier, a wooden frame, 3 magnetometer sensors, and 1 mechanical averaging drum had fundamentally altered the relationship between human decision-making and automated systems. No one recognizes that the principle of using fixed measurement points to classify incoming threats, the core concept of 1944, remains the operational foundation of the 2024 security infrastructure. The legacy of the harbor detection system was not technological dominance. 80 years of advancement had rendered the 1944 hardware obsolete. The legacy was epistemological. It was proof that vulnerability could be eliminated through rigorous measurement, that human decision-making could be augmented by reliable systems, that critical infrastructure could be secured not through increased personnel or increased firepower, but through understanding the physics of the threat and designing measurement systems that operated faster and more accurately than human operators. The principle remains unchanged. Measure the threat, classify the threat, respond to the classification. Everything else is implementation detail and refinement. The harbor detection system had revealed something profound about strategy and survival. The most significant innovations do not emerge from revolutionary technology. They emerge from the decision to measure, to automate, and to trust the measurement.